Hello, my name is Dmity Dremov. Our team took third place at the CA track. First of all, I want to tell a few words about ML Training's Moscow community. This community is dedicated to discussions and experience sharing in machine learning competitions. Members of our community successfully participated in this competition. 4 teams finished at top 10, including 2 prize places. Our solution consists of 5 stages: trainset transformation, edge filtration, features generation, edge probability prediction, and closure. Idea behind trainset transformation is to make trainset exactly the same size as the test set. This is an important part of our solution because filtration algorithms are implicitly dependent on the set scale. In order to do that, we split trainset to connect components and add components randomly until nodes count would be the same as in test set. Additionally, noise nodes added at random from distinct components as in the test set. We formed 2 such folds. These 2 folds in total have 80% of nodes available for training. Filtration is unsupervised algorithm. This algorithm selects a set of candidate edges of small size. Total number of potential edges in test set is about 5 billion. It's not practical to apply a machine learning algorithm for such a big set. 2 ideas are used for filtration: similarity of visited sites with nearest neighbors and shared rare URLs. United set of edges from both algorithms has recall about 53% and precision about 5%. In total, train set is about 4 million edges and test set is about 2 million edges. How visited URLs matrix is formed? For every visit, we count every prefix of an URL. For example, for Facebook.com messages, we take both Facebook.com and Facebook.com messages. After that, we do TF-IDF transformation and revise L2 normalization. Resulted sparse matrix is used for KNN with L2 distance. 15 nearest neighbors used. Some URLs are visited only by a limited number of devices. These devices are frequently linked. For every edge, we count URLs shared by less than 40 devices. We filter edges by weighted sum of URLs shared. URLs visited by smaller number of devices are more important and have bigger weight. Features can be roughly separated and based on visited URLs and based on visits time. Features based on the visited URLs use the same metrics as KNN filtration. We calculate distance between distributions of visited URLs with different metrics. L1, L2, L maximum, Kullback label divergence, and cosine similarity. For every edge, we calculate dot product of visited URLs vectors. For every edge in the resulted matrix, only URLs visited by both devices are non-zero. Rows of this matrix are used as sparse feature vectors. Also, SVD transformation of this matrix is used. First 40 components of SVD are used as features. Visits separated to 12 2-hours intraday buckets. For a pair of such distributions, we form 12 features as bucket differences. Additionally, we calculate sum of all 12 differences. Similar to that, for every 2 consecutive events, we calculate time interval and group them into 10 buckets. All intervals shorter than 2 seconds to the first bucket, from 2 to 5 seconds to the next bucket, and so on. Features are formed the same way as intraday features. Time window for every device is interval between first and last event. For every edge, intersection of such intervals is used as feature. Model to predict edge probability consists of 2 levels. Base models built out of fold, SVM and random forest built on the base level. XGBoost built on the meta level. Features of SVM model are rows from visited URLs matrix. SVM model is built separately for every number of filtration neighbor. Random forest model used with dense features. Meta features are all dense features, probability of random forest, SVM distance from decision boundary, and additional rank features. It's easier to explain how rank meta feature is calculated with the example. We have feature P and HAB. Also, we know values of this feature for all edges. If we sort all edges from A by feature P, AB would be second by rank among all edges. Rank of HAB by node B would be third. Finally, rank features for HAB with feature P would be 2 and 3. I want to summarize structure of edge prediction. With the filtered edges, SVM and random forest models are built. Predictions of these models with the basic and the rank features are meta features. Gradient boosting decision tree model is built with these features. Train set and test set consist of fully connected components. We use two ideas to extend edge set using this fact: transitive closure and fully connected components closure. In transitive closure, we count product of AB and AC probabilities. If product is greater than threshold, we add HBC. In fully connected components closure, we select set of edges with probability more than threshold. After that, we add all edges missing to form fully connected components. We combine top 97,000 edges by model prediction and additional 16,000 edges added by closure. Calculations. This solution was coded in Python with sklearn and XGBoost libraries. On the machine with 12 cores and 64 GB RAM, total work time was about 4 hours. I want to conclude. Strong side of this solution is edge probability modeling. Filtration and features are also good. Closure part could be easily upgraded to get better result. Thank you.